Detecting and pushing kidney stones or stone fragments without invasive surgery. Here, an ultrasound probe provides the pushing power in this lab demonstration at the Center for Industrial and Medical Ultrasound at the Applied Physics Laboratory, University of Washington. First task, find the stone.
Here it's the bright spot with the long tail, which is caused by ultrasound echo, just the vibrations of the stone. Find the right orientation. You can see that we're going to be pushing it out into an open fluid space right here. Once you have that, press the clear. And it shot right out of there. This is our training and development ultrasound phantom. It's made by a local company called Blue Phantom. Inside is an actual kidney phantom where the collection space is fluid filled. There's a glass bead that's about 5 millimeters in diameter that represents the kidney stone, and it shows up very well in ultrasound. So the system has several components to it. The first is the ultrasound probe. It's just a commercially available, this is an abdominal probe, a C5-2 from the HDI Phillips system. We have written software for it. It's all MATLAB-based software. It's very adaptable. We've been able to develop and make big jumps in our development along the way, while at the same time being able to collect valuable data for processing afterwards and helping to develop very useful algorithms for stone detection, as well as improving our capabilities of moving the stone in the system. We also have a suite of Doppler controls as well. And then we have our push controls. We can change our push frequency, we can change the duration of the push, the actual output level.
Oh good, nice, and not other calyx.
Urologist Matthew Sorensen tries his hand at the system, searching for and then moving a simulated kidney stone.
Nice.
There we go.
Nice. That went really far.
Yeah.
It's common for there to be leftover pieces or fragments or dust or gravel after we do a treatment for a stone. And sometimes those clear on their own, but oftentimes they don't. And they can grow into bigger stones that then require an additional treatment. And so one of the arguments in favor of this therapy is that it's not invasive, and we suspect it won't have much discomfort, and it'll allow us to clear out some of those fragments that tend to be left over. We haven't been able to detect any damage or any injury, and so it's essentially what we believe will be a safe and non-invasive way to treat these stones and stone fragments.
The amount of energy that it takes to move the stone doesn't turn out to be that much more than diagnostic levels. What we do is focus it down to a small point so it's concentrated, and we compress the amount of energy to a very short amount of time with a very high burst with a lot of off time afterwards.
We have a prototype at this point. We've submitted our letter to FDA and are in the process with them to get approval for a human feasibility study. So we want to demonstrate this works in people, may be able to do that even this summer. And at that point, we would look for a partner to commercialize this, or we'd actually start our own company to build pretty much the exact prototype that we have.
There we go.
Science at work for you. This is APL, the Applied Physics Laboratory at the University of Washington in Seattle.